So now it's time for lipids. Lipids here now. We don't find lipids in that form that we call polymers, and this is quite confusing. You could make a case to call a lipid a polymer because, as we're going to see, lipids consist of, most of them, a few parts stuck together, and that's kind of the general idea of polymers. But what you don't see in lipids is a whole bunch of them stuck together in a chain, like we just saw a starch is a whole bunch of glucoses in a chain. You don't see that with lipids, and when we get a structural formula up here in a minute, that'll be more apparent to you. Okay, so we don't typically call lipids polymers. It wouldn't be the worst mistake that you could make, but there you go. Okay, so what sets lipids apart from carbohydrates? Well, first of all, their molecular structure is not CH2O. And you know what? I'm going to have to go back. I'm going to do it right here because I meant to do it with the sucrose or a disaccharide. Sorry, I thought I silenced my phone. In fact, I know I did at one point, but it still is going to call. So anyway, call you later. So anyhow, sorry about that, but this makes it just like kind of real. So this, since you put two C6H12O6s together and take out a water, the formula for one of those things is going to be C12. You didn't take out any carbons, but you took out two H2Os. So instead of having 24 hydrogens, you only have 20. Not twice as many carbons, but it's the same basic kind of ratio. And then you took out two waters, each of which had an oxygen. So instead of 12 oxygens, you're going to have 10 oxygens. So this is the chemical formula for sucrose, right? And while it's not one carbon to every two hydrogens to every one oxygen, it's pretty close, and it's closer than any lipid is going to get, and it's closer than any protein or anything else. So it's still a recognizable thing to look at a chemical formula and see, is it at least pretty close to one carbon to every two hydrogens to every one oxygen? That means it's a carbohydrate, especially if it doesn't have any other elements like nitrogen or sulfur or anything like that. So here we go. Anyway, back to lipids. What makes them lipids? They're insoluble with water. What does that mean? Remember why water is good at dividing things? Because it's charged. What kind of things can it divide? Things that are charged. But lipids are basically uncharged kind of things because their atoms are put together mostly by covalent bonding that's not unequal sharing. That's non-polar. So they have little attraction. Affinity is a word you'll see for attraction here to water. That means they're not water soluble. That's the overriding category that causes we humans to put things in the lipid category, the overriding characteristic. And you're going to see that there's two kinds of lipids that don't look anything like each other, the glycerides and the sterols. What is common to both is that they're not water soluble, or at least not very much. Here's another vocab thing. Very common, and like on food labels, you won't see the word lipid. You'll see fats. But technically, fats are only one kind of lipid. But it's okay. We're gonna ignore the fact that often, very often, and even in test questions, you're gonna see fats referring to all lipids. Okay. Whew, that took a while. Okay, so here's a structural formula of a very simple glyceride type fat. Why do we call it a glyceride type? Because part of it is a glycerol. We would call glycerol then a monomer if it's by itself, not yet stuck to this thing, this fatty acid. We would call it a monomer, and we would also call this fatty acid a monomer. Here in this fatty acid, you can see, and if you remember, fatty acid was in the EOC syllabus list of words to know. So they might just give you a picture of a fatty acid and expect you to identify it not just as a lipid, but as a specific part called a fatty acid. You see a bunch of carbons. Remember I told you a chain of carbons that you saw in that glucose? when it was in its straight chain form. You might see somewhere else, but what don't you see here attached to those carbons? You don't see OHs, you don't see oxygens. So this is a pattern similar to some carbohydrate things, but dissimilar in the fact that you don't see the CH2O here. You just see carbons and hydrogens. This is therefore called a hydrocarbon chain as well. And then at one end of it, you see a group that I'm going to name real fast here and come back to later. This is called a carboxyl group. And you can see what part of it is, an OH. What is that good for? It's good for this dehydration synthesis thing. So if a fatty acid bumped into a glycerol like this, fatty acid will lose the OH, the glycerol would lose this H, they would become a water, and these two would become bonded right here, as you'll see in a second. Okay, this kind of glyceride fat would be called a monoglyceride because there's only one fatty acid to attach. But you can see on this glycerol, there's two other places where we could potentially attach two other fatty acids to make a triglyceride. And triglycerides, I think we're in the EOC syllabus thing. All right. But now let's take another look at this. Remember I said that in any molecule, where's the energy in a molecule? Well, it's in its bonds, right? But the energy that we can get out of a molecule is specifically more in the carbon-hydrogen bonds than it is in like carbon-oxygen bonds. So you can see here now why one characteristic of lipids is as it is. Gram for gram, a lipid has a little bit more than twice as much energy as a carbohydrate because look how many carbon-hydrogen bonds it has compared to like a glucose. It has a whole slew of them in this fatty acid part, and if that's the place where we can get energy from, it makes sense that a lipid would have more energy per gram than carbohydrates. Okay, so now here is a triglyceride, okay, and here it's all connected. We don't need to worry about that word, what kind of linkage that's called, but here's where the water was taken out. So to make this triglyceride, right, we had 1, 2, 3 water molecules were produced, one at each place where those fatty acids were connected to the glycerol, right? And you have here a molecule that's made of 4 monomers, right? However, again, we just by tradition don't call this a polymer because we're not going to add any more to it to make a long chain, and polymers kind of signify long chains. So that's this one. And now we're going to get to the idea that the bonds between carbons that we see a whole bunch of here, the bonds between carbons can all be single bonds, like they all are here in this picture. All of them are single bonds in this set of 3 fatty acids. That means what again? It means there's 2 electrons being shared there, 1 from each carbon, right? That's what a single bond is. Or it's possible that 2 carbons could be bonded by a double bond. I'll put one here. But if these 2 carbons were joined to each other by a double bond, that means they couldn't make the bonds with all these hydrogens because carbons only have 4 valence electrons. And look what this carbon has now, for instance. It has 1, 2, 3, 4, 5 lines around it, symbolizing 5 bonds. Carbon can't make 5 bonds. So for that double bond to happen, 2 of these hydrogens have to go away in the chemical process that would form that double bond. All right? This is the essence of what the words saturated and unsaturated refer to. It's the bonds between carbons. And the words specifically themselves actually refer to hydrogens. So this is a saturated fatty acid. What is it saturated with? Hydrogens. It holds as many hydrogens as it possibly can. That's what the word saturated means. But this one that I've modified is an unsaturated fatty acid. It doesn't have as many hydrogens as it can possibly because it's got this double bond. And these hydrogens had to go. So This is the difference between saturated and unsaturated fats, and you're probably familiar with the health difference. Health-wise, saturated fats are not as good for you as unsaturated fats, but this is a great example of science. In the last 20, 30 years, we've learned that it's not so much the fats that are bad for you as it is sugars. And we're going to come back to that in a little bit. So that, however, is the difference between saturated and unsaturated fats. Here's two models that don't have any C's, H's, and O's. They just have things that represent those atoms, right? And this is what happens when a double bond occurs between carbons. It also causes the molecule to bend. And this is part of why these unsaturated fats are not only not bad for you, they're actually good for you. What can be bad about a saturated fat that's made of these fatty acids, and it would be, again, 3 of them stuck to a glycerol, like in the last picture, is that they can kind of clump together tightly and clog up arteries because they stick to artery walls. But actually, what I'm going to tell you, what I've told you really kind of hinted at, is that it's when sugars attach to them that they get more sticky. So it's really sugars that are more the bad guys. Okay? So now we get back to this word fats. Fats are specifically now, organic molecule-wise, they are saturated lipids. Lipids that are composed of fatty acids that are saturated. If they're unsaturated like this one, more technically and commonly, we refer to them as oils. So another difference here, kingdom-wise, is that if you're an animal, you make these kind of fats when you put these lipid parts together. You make saturated fats, and you and I do that. But if you're a plant, like a corn plant, you make a lot of these kind of plants, and so corn oil is these unsaturated kinds. We have some kinds of oils that are even better for you than others. These are the kinds you find in fish, for instance, fish oil, and some other kinds of plants make omega-3 ones. What that simply means, what's omega mean? Omega is like the end of the Greek alphabet. So if that double bond that makes it unsaturated is in the 3rd carbon over, that's an omega-3 fatty acid. So that's where the 3 comes from in the omega. Hydrogenated trans fatty acids. These are bad ones. This is like Crisco. That stuff you might cook with that's kind of pasty white. Here's its story. It was made with corn oil, usually corn oil or some other kind of vegetable oil like canola. It was made with corn oil, but in the laboratory they then hydrogenated it. What's that mean? In this place where 2 hydrogens had to come out to make this double bond, and therefore to make this a little healthier kind of lipid, right? The hydrogens were put back in, and so basically they made them like saturated. But when they do that, they make a little different kind that we have learned is even worse for your health. It was not known when Crisco was invented, all this, but now it's known, and that's why the Food and Drug Administration has now mandated on food labels, they have to list how much, if any, trans fatty acids there are, because people are now becoming more aware that these are really bad fats, trans fatty acids. So what are the functions of lipids? Well, like carbohydrates, you make lipids in your cells, and so do plants, to store energy. And we already saw that they're even a better energy storage. They're like a deep storage form of energy. If you run low on carbohydrates, you start to use fats as energy. But they also have a function of forming the structural parts like we talked about of, like we didn't talk about, but of cell membranes, like this kind called a phospholipid, right? So now to contrast, because this gets confusing, because these 2 functions, energy storage and a structural function, are also functions of some carbohydrates. And the carbohydrate, a very common one, cellulose, that has a structural function is to make up cell walls. This phospholipid has a structural function to make up cell membranes, which are quite different than cell walls, but easy to confuse because they're all on the outside. If this is a cell membrane, the cell wall is going to be outside of that. Your cells and my cells don't have cell walls. Animal cells don't. All plant cells do. All fungus cells do. The cell walls are made of carbohydrate. The cell membranes are made of lipids, specifically these kind called phospholipids. Bunches of fat molecules in those kind of cells we call fat cells, help cushion organs and insulate. I don't think they'll ask you about those functions. But then there's other lipids, and these are the kinds that are quite different structurally. They don't look like this at all. We're coming up to them. They have the function of being like messenger molecules. That's what hormones are. So we'll get to those in a little bit. Okay. Now look here. If you're given this, and you quite literally, quite well could be given this, because phospholipids is a word that's in the syllabus. These are key organic molecules. They would expect you to be able to identify them as a lipid, as opposed to carbohydrate or protein, but also specifically as a phospholipid. So what are you looking for? Well, first, as a lipid, again, you have this long chain of carbons. How do you know they're carbons? Well, because they're an angle. There's lots of angles, right? This is the shorthand version, the abbreviated version of a hydrocarbon chain. Where are the hydrogens? Well, they're also understood. If there's nothing attached to these carbons, there really has to be something, and it's understood in biochemists that they're all hydrogens here. Okay? So you might recognize the 3 carbons that make up a glycerol chain. But to identify it as a phospholipid, you also identify this part. You won't find this in any carbohydrates, all right? But you are going to find it in nucleic acids. So if you see phosphate, that doesn't mean right away that, oh, this is a phospholipid. It's got to have all this lipid part along with it, okay? So real fast here, here's cholesterol. That's that kind of lipid that's called a sterol. You can see it looks quite a bit different than those triglycerides we saw. And it's not made by cells to store energy, but for another purpose. It also is what your cells start with to make molecules like this and other ones, like vitamin D. Your cells use cholesterol to make these sterol hormones, the ones that we call the sex hormones, specifically the male sex hormone testosterone, the female one estrogen or estradiol. And so not only is it a structural molecule, cholesterol, but it's also the kind of molecule we call a precursor. It's what you start with in your cells to make these molecules. Okay, and it becomes also an animal kingdom identifier because we're the only kind of things, living things that have cholesterol as part of our cells. Okay, so